Hello, everybody. I welcome you all to the day 6 of our Smart 25 Days Challenge. And today we are going to make our rock, paper, scissors smart contract. So, this would be we would be implementing the ages old rock, paper, scissors game in the form of a smart contract. And what is the use of that, you may ask? So, basically, when this game, you all know that this game is a very traditional game, but when coming up to the online part of playing such games in the real world scenario, these type of games involve two players, and at both of the players simultaneously reveal their moves, so it becomes very easy for each of them to conclude, okay, that there has been no cheating and fairly the game has been played, and the decision can be made. But when the online when we talk about playing such games online, there are many problems associated, such as the internet connection problem, or the trust issue can be there. There may be the interference by the intermediaries. So, to remove all them, we would try to make this game as secure as possible in this online scenario. And how we are going to do it, we'll see step by step. And I am going to take you forward with that. So, we'll see how we can create this case rock paper scissors game, and we'll also, by implementing this, we'll also see that how blockchain and web3 can go hand in hand with the gaming industry. So first of all, we'll create our new file that would be called as a rock paper scissors dot sol rock paper scissors dot sol. And then we'll smart writing our smart contract. As you know, our first line is spdx license identifier, and the second line is pragma solidity and the version of the compiler. Okay. Okay. Now we'll begin by writing the smart contract. So how we'll approach this problem is that we'll first need to see what our requirements are, and what is the best approach that we can think of. In this smart contract, we'll also keep a bet amount. This bet amount will act as a reward money for the person winning this rock paper scissors game. Okay, and we'll also make sure that both of them join by sending that required amount into this smart contract, and also specifying their move. We'll see how it can be done. We are first of all declaring three variables, that would be three constant variables that would be used for identifying the moves. For rock, it would be 1, and for paper it would be 2, and for scissors it would be 3. I hope it's clear, and these three variables will help any player play the game. Specify their move. Scissors. Now we'll define a struct for the player. Okay, so that struct would help us in keeping all the data related to a player in one place. I have told you before what is the purpose of structs in Solidity. If you have any confusion, then please go through my previous videos. We are just defining it with struct player, and the properties would be address of the player. We will require the address of the player who is playing this game. Then we'll also require a commitment. And what is a commitment? I'll explain it to you as we move forward. This would be used to for specifying the move, for storing the move which he will select out of 1 to 3, that is rock paper or scissors, and this is revealed. This is a Boolean variable that will keep track whether the player has revealed his move yet or not. So what we are going to do is, first of all, when the player will join with the specified required amount of bet and by specifying his move, so his move will not get stored onto the blockchain directly. Rather, it would be stored in the form of a commitment. And what is a commitment? A commitment is a keycack 256 hash of the sender's of the player's address along with its move. So what happens is, say, if one player has joined the game and he specifies his move, the other player will not know what move the first person has made. So this ensures that the other person cannot take advantage of knowing the move beforehand, and both of them cannot uh, change their moves once they have made it entered it into the form of commitment inside this game. So we'll see how we are doing this. Let us first declare our state variables. That would be here public player 1 and player 2, because we need only two players, so we'll keep it up to player 1 and player 2 only, so that no more players would be allowed to play the game at a single time. Bet amount to keep the track of bet amount, then to identify the winner, and then a boolean variable which will tell whether the game has finished or not. Now we'll define a constructor, and in that constructor we'll specify the bet amount while deploying the contract. Okay, constructor bet amount in ether. It will require first ask that the required amount should be greater than 0. If it's true, then it will proceed forward. Otherwise, it will show the error message as bet amount must be greater than 0. Now let us move forward, and we'll set the bet amount as this bet amount. We are setting this because the default value in Solidity is way, and for making it easy, we are keeping it in ether. So what we are going to do is the as amount would be specified in terms of the ether. How we are basically converting it into ether by multiplying it with one ether. So the person deploying the contract would just specify how many ethers would be the bet value, and if we say is one or two, so that amount would be converted into ethers because the default value is way. If we will not do this, so one would so while deploying the contract, when the person will specify one, so that would mean that one way only. But here, if now the person would specify the amount in ether, how? Because the default value was way, and we have converted that into ether. So now, while deploying the contract, if a person says provides the value 2, so that 2 means that 2 ethers. And how we have done that is quite simple, and it's shown here. Now we'll make our required functions. Now we'll proceed by making the required functions. That would be, first of all, the main function would be to join the game. And we are making the function join game. This function will take a new 256. Basically, if you do not specify 256 here, Solidity assumes it to be a uint 256 only by default, but it's better to specify. So that's why we specify here, and it will take a move as a argument. Okay, and move as a argument, and then it is a public payable function. It will first require that the message dot value, that the value of the transaction should be equal to the bet amount, should be equal to the bet amount, bet amount. Otherwise, it will show incorrect bet amount. amount equals. Uh, and one more thing which we can require here is that the move should be among 1, 2, or 3 only. Out of this 1, 2, or 3 only. Otherwise, it will show that invalid move. Otherwise, say a player may enter specify the value 4. So that should be an invalid move. So we'll require that the move should be 1, 2, or 3 only. Require that this move should be 1 or 2 or 3 only. Otherwise, it will show that it's an invalid move. So it will proceed from here, and now we'll assign the instances of the player struct their respective values. If the person is joining at the first place, so he would be assigned to player 1. How it's done is, first it will check if the player dot address equals to address dot zero. Address of 0 means ki the address is empty. Currently it has not been assigned any address, and address 0 is in the player address property of the player 1 instance of the player struct. I hope I am very clear that this player 1 is the instance of this player struct, and the player 1 dot address checks the address field of the player 1 instance, that it is whether it's 0 or not. So if player 1 dot address is 0, that means it has not been assigned to any address. So in the next line it will assign the player 1. And how we it will do is simple. The first property is the address, so it is here we are defining that message assign the message dot sender to the address property of the player 1 instance. Okay, this player 1 instance is the instance of this player struct, and here we are assigning the values to the player 1 instance. And how we are doing that is I am showing you here only. This is the commitment part. Okay, so this is a uh, 32 bytes. This is the fixed size byte array, and because here from this keycat 256 we'll get a fixed size array only, and fixed size hash value, and that hash value would be the hash of first ABI dot encode packed I have told you before only. So this is used to combine two or more values into a and make it into a single byte array. So make it into a single array. Okay, and then the keycat 256 will hash its value. By default, we are specifying that the move is 0, and we as we do not want to reveal the move, and we have set the boolean revealed as false. I hope it makes it very clear. And then we'll check the else if condition. That would be if player 1 has been already assigned, then check for player 2. In this we'll also see that we are specifying a required condition that will check if the same player tries to enter the game again. I know there is no motive for some person to enter the game twice, but we need to keep a check so that a single player may not enter by mistake 2 times into the game. Require that player one dot add address should not be the center of this message dot center. Otherwise, if it's true, then go on, and if it's false, then we'll say same player is not allowed to enter twice. Then we'll follow the same, just we'll make it player 2. Then if it's not the case, then we'll say both player 1 and player 2 have been assigned some address and their address is not 0, then we'll say that the game is full. Revert, game is full. So our join game function is complete, and now we'll make the function that is to reveal the move. This, what it is it will check that if when both the players have committed their moves, then only it will allow the players to reveal their moves, and one by one both the players can reveal their moves. And as soon as both of them reveal their moves, the smart contract will decide who won, and then it will distribute the staked amount respect accordingly, and the game would be resetted. And that's all. So how it's going to do it, we'll see here only. So reveal move will one more time ask the players to enter their move and specify what the move which they have played earlier while joining the game. This will require that the game should not be finished. Game finished. So game already finished. So, do you know why we are taking the not of this game finished? Because the basic property of require is that it will check this condition which is specified before this comma, and if this condition is true, then only it will allow to proceed forward to the next steps, otherwise it will show the error message. And in our case, we want that the game should be running when the player would be allowed to reveal his her move, and when the game would be game finish should be false. That means that the game should not have been finished. So when the game finished is actually false, which means the game is not yet finished, it will convert that to be true, because we are taking the not. And what this will help us in proceeding for to the next steps. Similarly, when the game has been actually finished, it would be true, and this not operator will convert that to be false. And that is what we want, because we want when the game has been finished, we do not want the person to try to reveal his move, and it will show the error message as game already finished. I hope I have made it clear that why we take this not operator, and do not just directly go for the condition. I will repeat once again to be more clear that this not operator helps us in achieving the desired outcome, and achieving the desired manner in which we want to proceed. And that is, we want to proceed if the game has not been finished. If the game is already finished, then we do not want the player to reveal the move. So what will happen is, in when the game is not finished, okay, that means that this game finished is actually false. What this not condition will do, this not condition will make it as true. And this means that yes, we will proceed forward, because that's what we want. And require condition will only allow us to proceed when this condition is true. Similarly, when the game finished is actually true, that yes, the game has been finished. So this not operator will make this whole condition as false, and this will help us in showing us this error message, that is that yes, the game already has been finished. I hope it makes it clear that why we use this not operator here. Now let us proceed forward and complete our reveal move. we'll create a instance of the player struct player storage. Why we are using the storage keyword is because we want to change the state of that player, which we are getting through this get player function. This function we have not yet made, and we'll make it after completing this reveal move function. It will be required that the player's address should be required that the player dot address should be contained, the message dot sender should be a address which is already contained in the player struct. Okay, it should not be apart from this, otherwise it will show that the player not found. Then it should also require that the player has not yet revealed the move. Otherwise it will show that the move has been already revealed. And which player we are talking about? The player which we'll get by calling this get player function. And we'll make this get player function just after completing this reveal move. So here we will check if both the players have committed or not. Otherwise, there can be a case where I am the first player and I have joined the game, and I may just reveal my move after joining the game without even thinking whether the other person has yet joined the game or not. So this check will ensure that first both of the players have committed their moves so that they can not make any changes to their moves in the future. This bytes 32 0 means that the bytes 32 array is not empty, which means that their commitment is not empty. And otherwise, it will show the error as both the players need to commit first. Now we'll check if this condition is true. That yes, the bytes 32, that commitment array is not empty. So we'll verify the commitment that whether the player is the player is revealing the move, and whether the move is same that he provided while joining the game or not. So what we are going to do is we are going to check both the commitments. We would be generating a commitment here too. Uh, uh, we would be generating a commitment here too. Commitment equals to, by using the same method, uh, sender's address and their move, and then we will check that both the commitment generated here and the commitment which was generated at the time when the player entered his move and did not reveal his move, they both should match. Then set the player dot reveal to be true, and player dot move to be the move which he has specified now. So let me clarify it once more. What is happening here is when the player joins the game, he will specify a move, but that move would not be stored to the blockchain directly. What will happen is the move would be stored in the form of a commitment to the blockchain, and that commitment is a 32 byte array that is 256 bits, and that is generated using the KiCac 256 hashing algorithm by and by hashing the message dot by hashing the value of message dot sender and its the player's move and the player's address. So basically we are hashing that value and storing that in the form of a commitment, okay, in the commitment field property of the player struct, so that the player may not change its move while revealing the move. What happens is when both the players have joined the game, so they will after joining the game they will reveal their moves one by one, and while revealing the move, to ensure that they do not change their move, we will compare both the commitments. So we would uh, we are what we are doing is we are creating a commitment here too, and by using the same method that their address and their move is being hashed by keycat 256, and that hash value is compared with the commitment which they provided while which we had made while the player had joined the game, okay. So the when the player joined the game, this commitment was made player dot commitment, and this commitment is being compared when the player is trying to reveal his move. Say if the person changes his move right now while revealing their move, so it will show so the both the values, this commitment value and the player dot commitment value will not match, and the error message invalid commitment would be shown. I hope it makes it very clear. And after that, we are specifying the fields. We are changing the fields to be true, and the move to that the player has revealed. Yes, the player has revealed their move. It becomes true, and the move is then specified to the move which the player provided originally while joining the game and while revealing the move, so they cannot change their move. This commitment helps us to ensure that the player cannot change their move while not specifying while not directly storing the move onto the blockchain when the player had joined the game. So I hope it makes it very clear that this helps us to make the game very secure, and so that the other player may not get any unfair advantage. So initially we had not stored the move directly, but we had stored that in the form of a commitment, and this ensures that the player does not change the move after both of them had made their commitments. So after this, we'll go to the next part, that is in this reveal move. Once both the players have revealed their moves, okay. So while we have set this to be yes, yeah, we have set it. So now what we want to do is we want to distribute the staked amount to the winner, and we want to store the address of the winner into this winner state variable. So how we are going to do it is, if both the players has revealed, player 1 dot reveal and player 2 dot reveal is true, then what will happen is this determine winner function would be called, and this function we are going to make just after writing this function. We have to make this get player function also and determine winner also. So these are helper functions which we need to make after this reveal move. So this reveal move function is now complete, and now we'll make our function that will help us to get the player by specifying its address. This would be a private function and a view function which will return the player, the the storage, because we want to make changes with the state of this player struct. Uh, so it will check that whether the player dot one's address is matching or the player dot two's address is matching with the provided address. If both of them are not matching, then it will say that the player is not found, player not found. Otherwise, it will return either player 1 or player 2. Okay. So if part is complete, then else if part player dot player 2 dot r equals to specified address, and player 2 else revert player 1 found. So now our get player function is also complete. Now we need to make the function to determine the winner, and to determine the winner we are going to proceed in the following manner. This would be a private function to private view, because it is not making any changes to the state. Returns address. If both the player 1 and player 2 make the same move, then the game would be a draw. So in that case, we'll assign that to be address 0. Then we'll return that no one won the game actually, or both of them won. You can take it either way. So we'll specify, and we'll return address 0. Else if else if, now this part is a very important part, and what it is doing is, it would be implementing the simple rules of a rock paper scissors game. That is, if player 1 chose rock, then the in which scenario the player 1 can win. So we'll see it here only. I will just code and tell you that is, you all know that if player 1 makes a move as a rock, so if player 1 chose rock, so he can only win when player 2 chooses scissors. Okay, so player 2 dot move should be scissors. Or player 1 can move, or player 1 can win when player 1 can win when player 1 chooses paper and the player 2 chooses rock. And 2 dot or player 1 dot move is scissors and the player 2 chooses paper. Then we'll move on to the else part of this game, that is otherwise it will return player 2 dot add. Oh, we have not yet specified what if this condition is true. Then return player 1 dot. Hmm. So first we have specified if both the players make the same move, then it's a draw. If player 1 can only win, player 1 wins. When these are the specified moves, okay, that player 1 chooses rock and player 2 chooses scissor, and or player 1 choose paper and player 2 choose rock, or the last case would be player 1 choosing scissors and player 2 choose if player 2 choose paper. So then only player 1 can win. So in that case, we'll return player one dot address, means the address of player one, and otherwise the address of player two. So this determine winner function is also complete, and now we'll make a function to distribute the winnings. So this we have made it correctly, and now we'll proceed forward with distribute winnings. If winner's address is blank or zero, not blank, zero, so then it means that it's a draw, and in that case we would be returning back the money and the staked amount of both the players. So to do that, we'll proceed in the following manner. Dot transfer bet amount, that is we are returning back the bet amount to player 1 and player 2. Else if else we are going to distribute the winning to the winner only. In the winnings amount is bet amount into 2, that is twice the betted amount. That's it. And after distributing the winning amount to the winners, then we will reset the game so that the game can be played again by some other players. So we have not yet made this reset game function, and this would be our last function, and we are going to create it just now. Yes, it's going to be a private function. This is going to make some changes with the state, and we'll keep previous winner variable to store. We are making the previous winner variable to store the address of the previous winner. Otherwise, what will happen as soon as we reset the game, the address of the winner will also get set to 0. So in that case, we will never be able to know the winner of the previous game. So that should not be the case. And for that, we are keeping a previous winner variable also. So all the fields would be resetted, but this previous winner will keep track of the winner of the previous game. So in this manner, we are resetting the both the instances of the player struct, player one and player two, and assigning them the zero values so that other players can assign them some values. Other players can play this game. Why we are doing this is to restore the previous winner so that we may know who was the winner of the previous game. Otherwise, that would also get vanished. And because as soon as both the players reveal their moves, what happens is the smart contract automatically distributes the winning and then resets the game. And while resetting, it will if we'll not keep track of the previous winner, then we'll never know the winner of the previous game, because as soon as both the players reveal their moves, the game gets reset. The amount get transferred to their respective accounts, and the winner gets the winning amount, and the game gets reset. So if the game gets reset, then we would not be able to know the winner. So to know the winner, are keeping this previous winner variable here. Otherwise, if we'll set this also to 0 or address 0, so we'll never know who was the winner of the previous game. So I hope this smart contract is now complete. We'll try to compile it. Hmm, we are getting some error here. If in the 64th line, that is get clear. We are getting the address. The oh, sorry. Here we are not comparing, we are basically assigning, and we need to compare it. So that is why that was a small error. Hope it runs now. Yes. So now we have compiled it, and we'll deploy it by specifying the bet amount in ether. Say we want the betting amount to be 2 ethers. Okay. So while deploying it, so now this contract has been deployed, and we can know that the bet amount is 2 ether. Okay. And here, say this is player one which wants to play the game, and he will join by specifying the move. What will happen is this player will need to send 2 ethers with his transaction, and then specifying the move. Say he chooses scissors, that is 3, and anyone can know what is the value for scissors, that is 3. For rock it's 1, and for paper it's 2. So he chooses 3 and then tries to join the game. So he provides 2 ethers and then tries to join the game. Now you can see the balance of the smart contract is 2 ETH, and this player 1, this you can check that this instance has been assigned the address of this player, and the commitment has been made, and its move is not showing because it has not been revealed. And in the revealed section you can see it's false, and the move is coming to be 0. And for player 2, no player has been assigned to player 2. So what will happen here is, now when some other player will try, say if this person, because we have kept a check, so this person will not be able to join again. And you can see if this person tries to join the game again, so there is, the error would be shown that same player is not allowed to enter twice. Which is good. And some other person now wants to enter this game. So this person is not aware of the move made by player 1, but is assured that player 1 has made its commitment. So uh, he must have played this game, and he must have moved, and his move can be anything out of the stone paper or scissor, out of this rock paper and scissor. So this person will just randomly pick any value. Say he picks rock, and along with this transaction he needs to send 2 ethers, and he will try to join the game. And now you can see the address, the balance of this smart contract is 4 ETH. So you can see that now player 2 must have assigned some address and some commitment. Oh, yes, in this instance, player 2 has been assigned the address of the player 2 only, that is this address. Okay, you can check the last digits, that are 02 dB, and here also it's player 2, it's 02 dB, correct? So what will happen now is these players will, for one by one, reveal their moves. So this person, we can start with player 2 only. So this person will say, yes, I played. I want to reveal my move now, and I made the move 1. So this will try to reveal its move, and now you can see it has been successfully revealed. And now the move is available for the public to see, and it is publicly changed, and it's the, now you can see that the move is 1, and yes, the player 2 has revealed their move. So now, but there is no use of this for player 1 because player 1 has already made its commitment. So now he cannot change his move, and let us see if he tries to change its move. And he had earlier made, uh, he had joined the game by making the move as 3, but now let us see, he wants to say that yes, I made the move as 2, and tries to reveal the move. Let us see what happens. Then it will show that it is a invalid commitment because the commitment produced here while revealing, okay, this commitment will not match the commitment of the player which he had made at the time of joining this game. So this shows us that once the player has joined with a particular move, he cannot change that, and that is the beauty of this commitment. That is why we are using this commitment here. And now when he will try to reveal the move with his original move, then he will be successfully able to reveal the move. And you can see that yes, player 1 and player 2, both of them can uh, both of them have revealed their move. So we will see that yes, uh, this address, this 202 dB, this address won the game. And why it won? And that's simple rule of stone paper scissor, because that guy chose rock and this guy chose scissors. So the guy who chose rock won this game. And the address, this for the this should have been transferred to the player 2, but let us see what's the error here. why the amount has not been transferred to this player. Okay, so here while revealing the move, it should, yeah, see. So after having a closer look, I figured it out. Actually, what is happening here is that we are specifying the winner by using the determine winner function, but we are never actually distributing the funds to the respective winner. Okay, so what we need to do here is we just need to add two lines here. That is, the we first need to say that yes, the game has been finished. True. We'll make this state variable game finished as true. This state variable game finished as true. And then we'll distribute the winnings. I hope now it will work correctly. So let us now again compile it and deploy it. Refresh it. Let's refresh it. And by using this address, okay, so let's specify the bet amount to be 2. See, say now this player only wants to play the game, and he makes the move to by specifying the value as 2 ether. Joined, yes, he has joined the game. Now some other person joins the game. I am playing scissors, specifying the value 2. Now he has joined, yes, both of them has joined. So now let us start revealing their moves. Okay, so now player 2 has revealed their move, player 1 has not yet revealed its move. And let us see while player 1 tries to reveal his move. So now you can see it's working properly, and the amount must so this game must have been resetted. And to know the winner, we can call this winner function, and it will show us that the winner of the previous game, which just now got over, was this address, this CB2. And we can check this address. Yes, this is now approximately 102 with us. So this guy won. So basically, that was it from my side, guys. Today, we made this rock, paper, scissors smart contract, and I hope you guys must have enjoyed it. And for your reference, I have provided these notes too. Okay, so you can go through them and you can see that what we have learned today. And I hope you guys enjoyed it. So let us meet on the day 7 of our smart 25 days challenge. And thank you guys for watching this video. Bye bye.